What if I told you we could reshape the entire world with just a circle? Every point transforms in perfect harmony. The closer ones move outward and the distant ones are pulled in, all guided by a single rule: symmetry. Even space itself bends and warps under its power, turning the infinite into something bounded and beautiful. This is geometry like you've never seen it before. Let's dive deeper into the elegance of inversion and projective geometry. Let's construct a circle with the center O. There's another point called A. Our goal is to find the image point of A if we take the inversion of the circle. This is a ray starting at O and passing through A. The inversion of the circle sends the point A to a point A star on this ray such that this equation is true. OA multiplied by OA star is equal to the radius square. In this case, A star is here. A star is directly dependent on A. What's interesting to notice is that A star and A are the same point if the distance OA is the radius. Let's use the same construction, but this time, let's see what happens when we perform the inversion 2 times. The first time, as we expected, the point becomes A star. The inversion the second time basically means that OA star times OA double star is R square. But that just means that both these equations have the same value. We can conclude that OA double star is equal to OA. After inverting the second time, the point A double star is just A. The point comes back to its starting place. Now we're going to sidetrack a little and talk about something important called the power of a point. Let's construct a circle and 4 points on the circle. After connecting the 4 points A, B, C, D and the diagonals, we have a cyclic quadrilateral, which is basically a quadrilateral where all the 4 points lie on a circle. Now I'm not going to go into depth here because this is a big and beautiful topic on its own, but it is pretty easy to notice that there are quite a few similar triangles here. If we shift P like this, they are easier to notice. And because of the similarity, we can construct an equation. When A, B, C, D are the points of a cyclic quadrilateral and P is the point where the diagonals meet, then PA times PB is equal to PC times PD. This is the power of a point. And it turns out the converse is true too. When PA times PB is equal to PC times PD, ABCD is a cyclic quadrilateral, and that's what we're going to use. If we have 2 points A and B, and we perform the inversion of a circle, these points become A star and B star. Since we know OA times OA star is equal to R square, and OB times OB star is equal to R square, we know that OA times OA star is equal to OB times OB star. Using the converse of the power of a point, we know that A star, B star is a cyclic quadrilateral. That means they all lie on a circle. Pretty neat. Another cool point is that you can perform an inversion when there's a whole circle inside. Then after the inversion, the small circle will be projected outside into a bigger circle. The coolest part is that it stays a circle even after the inversion. If the center of our original circle is on the smaller yellow circle, then after the inversion, the yellow circle will be projected to a line. One can also imagine this as a circle with a radius of infinity. This makes our lives in Math Olympiad problems a whole lot easier, because it is much easier to work with a line than with a circle. That's all I have for this video. I made this because I found circle inversions very interesting, and they can be an amazing tool in competitions. This is an interesting subtopic of projective geometry, which I hope I'm eventually going to make a video on. I thank you all for watching this video.